Paper name is Operations Research and Optimization Technique for the MCA courses. Paper code is MCA 304. For the BTech courses, paper name is Operations Research and paper code is CS 505A. Today lecture class is the lecture 10. We learned the linear programming problem model. We learned the primal to dual. Today is the lecture class 10 under the linear programming problem. Today we learn how to find out the dual of a primal of a linear programming problem. Previous class we already discussed how to find out the dual from the primal of a linear programming problem. Today also we discuss the few examples, and that is the particular very special types of the examples where the few one inequations is basically the equations and one variable is a unrestricted inside. We know in any unrestricted variable we can express is a difference of a two restricted variables. Suppose x is a unrestricted variable, then we can express x is the difference of x dash minus x double dash, where x dash and x double dash are greater than equal to 0. For equations, we have to break it into the two weak inequations, less than equal to and greater than equal to. For finding the canonical form, for the maximization problem, less than equal to, you have to convert to the greater than equal to, you have to convert to the less than equal to by multiplying both sides by minus 1. For the minimization problem, canonical form, less than equal to type, you have to convert it to the greater than equal to type by multiplying both sides by minus 1. Let us consider a problem. You have to find out the dual of the following primal. Minimize z is equal to 2x2 plus 5x3. x1 is not there. Subject to the conditions x1 plus x2 greater than equal to 2, 2x1 plus x2 plus 6x3 less than equal to 6. Since it is a minimization problem, so less than equal to constant, we have to convert it to the greater than equal to. Again, x1 minus x2 plus 3x3 is equal to 4. This is a equation. That equation we have break it into the two inequations. One will be greater than equal to 4, another will be less than equal to 4. We have the 2 less than equal to 4, that we have to convert it to the greater than equal to by multiplying both sides by the minus 1. So we move the solution by step, and all the variables x1, x2, x3 are greater than equal to 0 for the given problem. That given problem is known as the primal. We have to find out the dual of the given primal. Since the given primal problem is not in the canonical form, we interchange the inequality of the constants. Inequality means the second constant is not greater than equal to, it is less than equal to. That we have to convert to the greater than equal to by multiplying both sides by the minus 1. Also, the third constant is an equation. This equation can be converted into the two inequations. So, rewriting the given problem, primal, will get minimize z is equal to 0x1 plus 2x2 plus 5x3. Subject to x1 plus x2 plus 0x3 greater than equal to 2 minus 2x1 minus x2 minus 6x3 greater than equal to 6. x1 minus x2 plus 3x3 less than equal to 4, and another inequation is x1 minus x2 plus 3x3 greater than equal to 4. x1, x2, x3 greater than equal to 0. Now, third constant is not satisfying our the canonical form, that we have convert into the greater than equal to inequation type by multiplying both sides by the minus 1. Again, we are rewriting this problem we get. Again, that is the mistake one. Since this is 6, so when you are multiplying both sides by -1, so that should be in the next form will be -6. So this will be the -6. Obviously, this should be the -6. In the next table, it is the -6. And x1 minus x2 plus 3x3 greater than equal to 4. And next constant we are changing is minus x1 plus x2, changing the sign, minus 3x3 greater than equal to minus 4. And x1, x2, x3 greater than equal to 0. Now here, how many constant is there? That many dual variables will be in the dual problem. Since here the 4 constants, we take W1, W2, and we got these two inequations from the one equation. In this case, we are considering the two variable as W3 dash and W3 double dash. Obviously, these two will be combined and we will get the W3. So when the constraint is like that, if we back to the original problem, see, in this case, choosing the dual variable in such a way, W1 for this or Y1 for this, W2 for this, and in this equation we are converting to the two inequations. For one equation it would be W3 dash, and another inequations it would be corresponding to that, it would be W3 double dash. Because for that we know if any constant is holding the equality sign, corresponding dual variable will be unrestricted in sign. If any variable in the primal is unrestricted in sign, corresponding constant will be the holding the equality sign. Due to that, keep in mind, we should choose the variable like that. Since there are the four constraints in the primal, we have the four dual variables. Let W1, W2, W3 dash, W3 double dash be the dual variables. Then the dual of the primal is. So we can write in this way by converting. How we can write? From this. W1, 1 W1 minus 2 W2, 1 W3 dash minus W3 double dash. It is minimization problem, so that will be the maximization problem, less than equal to this coefficient 0. Again 1 W1 minus 1 W2 minus 1 W3 dash plus W3 double dash less than equal to 2, and third constant will be 0 into W1 minus 6 into W2 plus 3 into W3 dash minus 3 into W3 double dash less than equal to 5. And Z function will be maximize. Z function will be maximize W, or Z1 we can write any other variable, that would be the maximize 2 W1 minus 6 W2 4 W3 dash minus 4 W3 double dash. And X, instead of this we will get W1, W2, W3 dash and W3 double dash greater than equal to 0. Now W1 minus 2W dash plus W3 less than equal to 0, less than equal to, and these 4 are greater than equal to 0. Let combining these two variables W3 dash minus W3 double dash, these two are greater than equal to 0, satisfying the non-negativity condition, and we are considering W3 is equal to W3 dash minus W3 double dash be unrestricted in sign. Then we get maximize Z dash equal to 2W1 minus 6W2, and combining W3 dash minus the W3 double dash, we will get 4W3. Subject to the constraint W1 minus 2W2 plus W3 less than equal to 0, combining W3 dash minus W3 double dash in the third variable W3. Second constraint is W1 minus W2 minus W3 less than equal to 2. 0W1 minus 6W2 plus 3W3 less than equal to 5. Now we get W1, W2 greater than equal to 0, and W3 is the difference of the two restricted variable is greater than equal to 0. That's why W3 is unrestricted in sign. So this is the dual of the given problem. Let us consider another example. Find the dual of the following LPP. Maximize z equal to 2 plus x plus 2y subject to the constraint 2x plus 3y greater than equal to 0, 3x plus 4y equal to 5. Let's see, the first constraint is not satisfying the canonical form. So 2x plus 3y we have to convert to the less than equal to form by multiplying both sides by the minus 1. Again, second constraint is a equation that you have to convert into the two inequations. One will be greater than equal to 5, another will be less than equal to 5. Here the two variable is that x is greater than equal to 0 and y is unrestricted in sign. For this, y we have to consider the y dash, difference of y dash and y double dash, where y dash and y double dash is greater than equal to 0. Now move to the solution. Since the second constraint is an equation, this equation can be converted into the two inequations. One will be less than equal to 5, another will be greater than equal to 5. And as y is unrestricted in sign, so y we can write in the difference of the two restricted variable as y equal to y dash minus y double dash, where y dash and y double dash greater than equal to 0. So this problem we can rewrite by introducing y dash and y double dash and breaking this. So max z equal to x plus 2 into y dash minus y double dash subject to the constraint minus 2x minus 3 y dash minus y double dash less than equal to 4. 3x plus 4 y dash minus y double dash less than equal to 5. 3x plus 4 into y dash minus y double dash greater than equal to 5. And here is the three variables x, y dash and y double dash, all are greater than equal to 0. Now, how many constraints we have here? 3. But last two constraints we got from an equation. So when we are choosing the dual variable, so dual variable will be 3, as there are the three constraints in the primal. Let W1, W2 dash and W2 double dash be the dual variable for the dual problem. This is the maximization problem, so it would be converted to the minimization problem. And objective function will be minus 4 W1, 5 W2 dash plus 5 W2 double dash. First constraint will be, we have to consider this way, minus 2 W1, 3 W2 dash plus 3. This actually maximization problem. So before that, we have to convert it, the third constraint, by multiplying both sides by the minus 1. because it is not satisfying the canonical form. So before start the dual problem, you have to convert the third constant by multiplying both sides by the -1. So rewriting this given primal, we get max z is equal to x plus 2y dash minus 2y double dash minus 2x minus 3y dash plus 3y double dash less than equal to -4. 3x plus 4y dash minus 4y double dash less than equal to 5. Now multiplying the third constant by -1, we will get minus 3x minus 4y dash plus 4y double dash less than equal to -5. X, y dash and y double dash greater than equal to 0. Since there are the three constraints in the primal problem, then there be the three variables in the dual problem. Let W1, W2 dash and W2 double dash be the dual variables. Then there are the three variables in the, since there are the three variables in the primal, then we will get the three constants in the dual. Now the dual of the primal is z dash minus 4w1 plus 5w2 dash minus 5w2 double dash c. So objective function will be minus 4w1 5w2 dash minus 5w2 double dash. This is our the objective function that will be minimization. Minimize w, capital W you can write, or we can write the z1 or z dash or z star. And first constant will be minus 2w1 plus 3w2 dash minus 3w2 double dash. Say, and it is, this is the minimization problem, new one. So this will be greater than equal to 1. Second constant will be minus 3w1 plus 4w2 dash minus 4w2 double dash greater than equal to 2. Third constant will be 3w1 minus 4w2 dash plus 4w2 double dash greater than equal to minus 2. So when we are doing in the paper, just put it a line here and write here w1 working variable, w2 dash and w2 double dash. Then it will be easy to form the dual from this table. From the, if we consider the coefficient matrix, and this B goes to here and that C come here. Now z dash is equal to, I already explained, minus 4w1 plus 5w2 dash minus 5w2 double dash. Subject to the constraint minus 2w1 minus 3w2 dash minus 3w2 double dash greater than equal to 1. Minus 3w1 minus 3w1 plus 4w2 dash minus 4w2 double dash greater than equal to 2. 3w1 minus 4w2 dash plus 4w2 double dash greater than equal to minus 2. And w1, w2, this should be the w2 single dash, comma w2 double dash greater than equal to 0. This should be the single dash greater than equal to 0. Now let w2 equal to difference of w2 dash minus w2 double dash, where w2 dash and w2 double dash greater than equal to 0. So as we consider w2 is the difference of the two restricted variable w2 dash and w2 double dash, so w2 becomes a unrestricted variable in sign. Let w2 is equal to w2 dash minus w2 double dash, so that the dual variable w2 is unrestricted in sign. The final dual of the primal is minimization z1, or we can write Z1 here, Z star, or we can write the capital W equal to minus 4W1 plus 5 W2 dash minus 5 W2 double dash minus 2 W1 plus 3 W2 dash minus W2 double dash. By grouping we are getting greater than equal to 1 minus 3 W1 plus 4 W2 dash minus, this should be the W2 double dash, this is W2 double dash, this should be the W2 double dash greater than equal to 2 greater than equal to minus 2. Now changing this difference by W2 will get the final result. That is mean Z1 equal to minus 4W1 plus 5W2 minus 2W1 plus 3W2 greater than equal to 1 minus 3W1 plus 4W2 greater than equal to 2 3W1 minus 4W2 greater than equal to minus 2 W1 greater than 0 and W2 is unrestricted in sign. But it is better when we are writing the final dual of the primal, we should not keep the minus value in the right hand side. So it is better if we convert it multiplying both sides by the minus 1. That means minus 3W1 plus 4W2 less than equal to 2. So final dual of the primal. See, minus 4W1 plus W2, this is so minus 3W1. See, by multiplying this is, we will get minus 3W1 plus 4W2 less than equal to 2. That is it. So in this case, we are getting, we can write here also. So in this case, we are getting W2 is unrestricted in sign and W2 is greater than equal to 1. Now see, if we combine this, what we will get? By combining this, left hand side is the same. One is greater than equal to 2, another is less than equal to 2. So combining these two, we will get a equation. So final dual of the primal is minimize Z1 equal to minus 4W1 plus 5W2. Combining these two in equations, we will getting a equation subject to the constraint minus 2W1 plus 3W2 greater than equal to 1, and this is equal to 2 minus 3W1 plus 4W2 equal to 2. W1 greater than equal to 0 and W2 is unrestricted in sign. Let us consider another example. We have to find out the dual of the given primal. This last two and this problem is the combination of the equation and one variable is unrestricted in time. So as we learn, directly we can write the dual, but we should not write that. If it is the concept is clear, then we can directly write the dual of that. We know when the constraint in the primal is holding the equality sign, corresponding variable will be unrestricted in sign. We can verify our result from here. See, when we are considering, so our variable equality, if we consider this is our the W1. When we break it into the two in equation, that time we consider W1 dash and W1 double dash. But in this situation, we can consider corresponding dual variable is W1. Corresponding to this W2 and corresponding this W3. x3, see x3 is unrestricted sign. So x3 we replace by x3 dash minus x3 double dash. That means x3 we are considering as a difference of the two restricted variable as x3 dash minus x3 double dash, where x3 dash and x3 double dash are restricted variable greater than equal to 0. So corresponding the constraint corresponding to x3 will get the equality constraint. So from that directly we can write that. So whatever the dual we will get, we can verify that. First variable our will be the unrestricted sign, and third constant holding the equality sign. From the given problem, this is not the plus, this should be x1 comma x2 greater than equal to 0 and x3 is unrestricted sign. Since the variable x3 is unrestricted in sign, we can replace x3 by x3 dash minus x3 double dash, where x3 dash and x3 double dash are greater than equal to 0. Also bring the problem into the canonical form 65, that means the second, this second one, this is the minimization problem. For the canonical form, this should be greater than equal to 65. And after breaking it, one will be the less than equal to, another will be greater than equal to. So less than equal to, you have converted to the greater than equal to by multiplying both sides by 1. And also same time we are replacing x3 by x3 dash minus x3 double dash. So first constraint is less than equal to 22, also greater than equal to 22. Since it is a minimization problem, so first constraint we have to convert it to the greater than equal to by multiplying both sides by minus 1. And third constraint was there the less than equal to, so it is also converting to the greater than equal to by multiplying both sides by the 1. And this is already greater than equal to 120. Our variable is x1, x2, x3 dash. This is not the minus, this should be comma, x3 dash, comma, x3 double dash greater than equal to 0. Rewriting this problem again, minimize z, 4x1 plus 5x2 minus 3x3 dash plus 3x3 double dash. This is our the objective function. X1 plus x2 plus x3 dash minus x3 double dash greater than equal to 22. Minus x1 minus x2 minus x3 dash plus x3 double dash. All will be negative and this is negative. This will be positive greater than equal to minus 22. Minus 3x1 minus 5x2 plus 2x3 dash minus 2x3 double dash greater than equal to minus 65. x1 plus 7x2 plus 4x3 dash minus 4x3 double dash greater than equal to 120. In this case, considering the dual variable w1 dash w1 double dash, this is w2 and this is w3, and rewriting the, now writing the dual of the given problem, will get. So objective function will be 22 w1 dash minus 22 w1 double dash minus 65 w2 1 plus 120 w3. This is the objective function. And one constraint I am saying, suppose the second constraint, I am considering the second constraint, 1 into w1 dash minus 1 into w1 double dash minus 5 w2 plus 7 w3, and that is maximization problem, so less than equal to 5. Second constraint. For verification, move to the next line. Since there are the four constraints in the primal problem, in the dual there are the four variables, namely we are considering W1 dash, W1 double dash, W2 and W3, so that the dual is given by max Z dash is equal to 22 W1 dash minus W1 double dash minus 65 W2 plus 120 W3. Subject to the constraint, I already set this one verified. W1 dash minus W1 double dash minus 5 W2 plus 7 W3 less than equal to 5. Now again I am saying the all constant H. First one, W1 minus W1 dash minus W1 double dash minus 3 W2 plus W3. Second one, this is less than equal to 4. Third one I am saying 1 W1 dash minus W1 double dash plus 2 W2 plus 4 W3 less than equal to minus 3. Same constant we will get with the negative sign. Minus W1 dash plus W1 double dash minus 2 W2 minus 4 W3 less than equal to 3. So second one we have to, third one we have to convert. Again rewriting we will get less than equal to minus 3. Minus W1 plus W1 dash W2 double dash this is rewriting the two times W1 dash W1 double dash W2 minus W3 greater than equal to 0. After converting this one, we are rewriting here. So this equation will be changed and this will be greater than equal to, this is not less than equal to. And last one is the structure. So this is rewriting this by multiplying both sides by minus 1 and combining this should be greater than equal to 1. Combining these two, we will get the equation. W1 dash, W1 double dash, W2 and W3. Now we replace the W1 dash minus W1 double dash by the W difference of this W1. So let's W1 equal to W1 dash minus W1 double dash, where W1 dash and W1 double dash are greater than equal to 0. Then replacing this by W1 we will get, and when we are replacing this by W1, so W1 will be unrestricted in sign. Let W1 equal to W1 dash minus W1 double dash. This will be the single one. That is, the variable W1 is unrestricted in sign. So max Z dash equal to 22 into W1 dash minus W1 double dash minus 65 W2 plus 120 W3. This is we are writing in a grouping format, W1 dash minus W1 double dash. Now it is replacing W1 dash minus W1 double dash by W1, we get max Z dash, this is 22 W1 minus 65 W2 plus 120 W3, and W1 minus 3 W2 plus W3 less than equal to 4, W1 minus 5 W2 plus 7 W3 less than equal to 5, Now these two constraints, left hand side is the same, one is greater than equal to 3, other is less than equal to 3. So now combining this we will get this is equal to a equation. Combining these two inequality we will get an equation, and where we can write W1, W2 and W3. W2 and W3 is greater than equal to 0 and W1 is unrestricted in sign. So this is our the final dual of the given primal. Mean Z dash equal to 22W1 minus 65W2 plus 120 W3 subject to W1 minus 3W2 plus 4W3 less than equal to 4. W1 minus 4W2 plus 7W3 less than equal to 5. And minus W1 minus 2W2 minus 4W3 is equal to 3. Where W2 and W3 greater than equal to 0 and W1 is unrestricted in sign. So this is the end of the class of finding the primal to dual, and at the same time it is the linear programming problem. Whatever contains in your syllabus, that is also the complete. Next we learn in the lecture class 11, that is the transportation problem. First we learn introduction to the transportation problem. Transportation problem in short form we can write the TP, transportation problem. Transportation problem is a class of LPP. Now we show the transportation problem is a class of the LPP. LPP means transportation problem should have one objective function and the constants, all the constants and the objective function should be linear. Then it is known as the linear programming problem. Then we learn the general form of a transportation problem, rules to finding the initial basic feasible solution, and how to find out the initial basic feasible solution. That the few methods is there that we learned in the first class. We learned the northwest corner, and what is called the initial basic feasible solution, that we already learned in the linear programming problem, and we learned when we solve the simplex method. First we got the initial basic feasible solution. That initial feasible solution we improve to find the optimum solution. So this is the end of the today's class.